Section 2.4 Continuing random variables. Many random variables are continuous. For example, the speed of a car that can have a values in between 0 and 90 miles per hour on the highway, but we can find cars that are traveling to any value in between those, for example 82.3 miles per hour. Another example is the concentration of a chemical in a water sample. It could be a percentage, and the percentage it's a real number. Tensile strengths that are given in pascals in a test. Heights of people in a population, lengths or areas of manufacture components, measurement errors, electricity consumption in kilowatt hours, etc. So, what is a continuous random variable? A continuous random variable is a random variable that can take on any value in a range, and that range could be infinite. If the random variable is continuous, the probability cannot be described in terms of probability mass function. It is not concentrated at one single point, but is distributed. Instead, a probability density function for the random variable is used. Also, it is called probability distribution. The probabilities of random variables are given by areas under the curve, and the function f of x is the probability density function of x, as we can see in this example. So instead of having the value of the probability at certain points, we have a continuous distribution. And if we want to compute the probability at one range, we have to compute the corresponding area. So one of the main properties of the probability density function is that the integral from minus infinity to infinity of f of x dx is equal to 1. Also, f of x is greater or equal to 0 for all x. How do we compute the probabilities? Let's suppose that x is a continuous random variable with probability density function f of x, and a and b are two numbers with a less than b. Now, the probability of x to be in between a and b is equal to the integral from a to b of f of x dx. So let's locate a at one point at b, which is greater than a. So the probability of x being in this range is equal to the area under the curve in between a and b. Now, the probability of x being less or equal to a, it will be the area under the curve from minus infinity to a. And the probability that x is greater or equal to a, it will be the area under the curve from a to infinity. The cumulative density function f of x is defined as the probability of the variable x being less or equal to x. So therefore is defined as the integral from minus infinity to x of f of t dt. If x is located at this point, that cumulative density function is equal to the area underneath the curve at that point. So if this is the cumulative density function at point x, the value at x is the area underneath the PDF. Well, the main advantage of having the cumulative density function is that it avoids computing the integrals, and that could be nice sometimes. Now let's have a look at the definition of mean and variance for continuous variables. So if x is a continuous random variable and f of x, the probability density function, the population mean and variance are defined as mu is equal to the integral from minus infinity to infinity, that's the whole domain, of x multiplied by f of x dx. If you remember from your statics and dynamics courses, so this is the actual definition of the centroid. In this particular case, the mean is going to be located at 0. Now, the variance is defined as the integral of the square square of the difference from x to mu multiplied by f of x. Now the interesting thing about the variance is that it's measuring how sparse is our function. So if we have a function that has this shape, the variance is a measure of the sparsity of our function. So this will have a variance which is less than the variance of the one in black. Additionally, the variance can be computed as the integral from minus infinity to infinity of x squared multiplied by f of x dx minus mu squared.